Okay, so in this lecture, we'll look at sensitivity analysis, which is a continuation of the interpretation or the post-optimality analysis, right? So we say that the sensitivity analysis is the analysis of the parameter changes and their effects on linear programming solutions, right? Their effect on linear programming solutions. So the different categories of the parameters changes that we consider are the change in the right-hand side and the change in the objective function, right? So what happens if we change the BIs and what happens if we change the right-hand side values, right? So let's take an example. So assuming we want to maximize this of our normal example, which is subject to labor, material resources, and also storage, right? So we solved this earlier on, so we are familiar with this solution, right? So assuming we want to say that there is an increase in one of the BI values, right? One of the BI values. So these are the BIs, and these are the AIGs, right? Good. AIG, so it's 1, 1, and it's 1, 2. So that is row 1, column 1, and row 1, column 2, right? And this one will be row 2, column 1, and this one is row 2, column 2. So this one is row 3, column 1, and this one is row 3, column 2. Something like that, right? That's what it means by the AIGs. Okay, the activity. So assuming there is an increase in one of the BI values, for instance, labor from 10 to 12 by an amount, can it affect the final solution? Right? Can it affect the final solution? So this is what we want to do. So the feasible solution space may change to the point where the optimal solution basis also changes, right? So the Z value can change to the extent that sometimes when it changes, it affects the strategy. That is the main X1, X2 values, right? That's what it means. So the general approach for determining the range of BI values for which the solution B remains optimal will be presented, right? Okay, so take this example. Now, a general increase in the right-hand side value of the labor constraint by an amount we don't know. So a change will result in the following. So this is the initial solution, or this is the initial problem where we have x1 plus 2, x2 is less than or equal to 10, right? So assuming that there is an increase in the right-hand side, or there's a change, right? We are representing that by the delta sign, right? Good. So we add each of them, and we are saying that it's only, so this one is when a change in the labor, which is the first one, right? And so this is the material. So we are holding the rest constants, right? We are holding these two constants. That's why we said there's no change 0 and there's no change here. All right, so you see that the initial tableau using the updated constraints. So we want to understand this. So I'm taking it from this direction, right? Okay, so the initial tableau is represented in this form, right? So we have x1, s2, s3, and the BIs become 10 plus a change, 36 plus no change, 40 plus no change, right? All right, so if we are to patiently go through this exercise, right? So we'll see that the change in the BI column are the same as the values in the SI column, right? So the corresponding final tableau or the optimal tableau will be this. So x2 will be 4 plus a change, x1 will be 2 minus 1 change, and s3 will be 8 plus for change, right? And the ZJ will plus 28 plus this change. All right. So the same effect is also observed in the optimal tableau, right? The same effect where we have the change occurring in the BIs, right? So this is how we go about it. So in effect, the coefficient of the change in the final tableau, right? The coefficient of the change in the final tableau are the same as the values in the SI column, right? The same as the values in the SI column. What are the values in the SI column? We can see here, all right? Good. So it is therefore unnecessary to go through the entire simplex process. This is key, it's very significant here. So when you're looking at the change in the BIs, you don't need to go through the entire initial solution and solve the tableau, do your iterations, and no, there's no need to go through the entire problem, right? So in general, it is only necessary to change the final BI values by a multiple of change, right? Where the multiple is the column coefficient of the slack variable. So let's look at it. So you see the column coefficient of the slack variable. So we have S1 here, and we have S2, and we also have S3, which is in solution, right? Good. So what it means that X2 becomes 4 plus 1 change. X1 is 2 minus change, and S3 is 8, right? So the variables that we are talking about are this. So you see that these values never changed, right? Apart from the changes that were changing, right? However, the S3 value here was 0 in the marginal value, which is this, right? Was 0. Okay. And X1 is also 0, S2 is also 0. Okay. So this is what we are saying. There is no change in this BI value. So what we'll do is then to say that the simplest method requires that all the feasible solution values to be non-zero, right? Should be non-zero. Therefore, it means that in order to determine the range of feasibilities of BI, the range of feasibility of VI, so the values of BI that will still maintain the solution as optimal, right? So the following inequalities are solved simultaneously. So the X2 value, right, is 4 plus delta greater than or equal to 0, right? That means that the delta is greater than or equal to minus 4 if you are to work it out. 2 minus the change greater than or equal to 0. So the delta is 2, and 8 plus 4 is equal to that, and the delta is that. So combining these three inequalities, right, we'll see that -2 less or equal delta and that. So this is what it means. So assuming we go to the elementary, right, where we have our number line, right, and we have our 0 here, and assume we have 2 and we have 4, -2, -4, -6, right? So for the first constraints, I can change the color of my marker and use blue. So the first constraint says that it's greater than or equal to -4. So it means that here, anything that goes in this direction is greater than or equal to -4. The second constraint is less than or equal to 2. So I do this, anything that goes this direction less than or equal to 2. And the third one is t is greater than or equal to 0, -2. So anything here is greater than or equal to -2. So it is very clear that from -2 to 2 is the boundary that satisfies all the three constraints. That's why we say that then the delta will lie between -2 is greater than -2, but cannot exceed 2 with 2 inclusive. So this is how this comes about, right? Very simple. All right. So to find the range of BI values, right? Remember that the labor constraints, right? The labor constraint was actually less than or equal to 10 for labor. And we say that if you are to look for a change, then it's 10 plus the delta, right? So we are saying that if the BI is actually, if the BI is actually 10 plus the delta, which is the labor, then it means that the delta is actually BI minus 10. So when we place our delta into our -2 is less than or equal to delta, less than or equal to 2, then it's -2 less than or equal to BI minus 10. That, so we have -2 plus 10, right? And BI 2 plus 10. So we have 8 BI and we have 12. All right, so you see that the change will actually be between 8 and 12, right? So this means that the variables in the optimal basis will remain feasible as long as BI is between 8 and 12, right? And what was the BI? The BI was 10, right? So the constraint itself was x1 plus 2x2 is less than or equal to 10. So you say that the solution will remain feasible as long as our resources is between 8 and 12. This is what it means, in between 8 and 12. All right, so that's very simple, right? So what about if there are changes in the objective function, right? If there are changes in the objective function, so changes in the profit or the cost contribution, right, in the objective function can also occur for a basic or non-basic variable. That is whether the variable is in solution or not, right? So the following example will be used to demonstrate scientific analysis for the CG. That is the CJ when xj is a non-basic variable, when it is not in the basic solution. So this is the example that we'll deal with, right? So if we are to analyze this, we'll see that the slope of the objective function actually depends on the value of the CJ. Hence, a change in the CJ can affect the optimality of the original solution. So we'll examine the range of CJ over the present solution and will remain optimal. So let's observe this final tableau. So this is a final tableau that we want to observe, right? The final tableau. So we want to say that with this final tableau, if there is an increase in the value of C2, right? So this is C1 and this is C2, right? Good. So if there is a change in the C2, that is 4 plus change, it can be positive or negative, right? All right. So the solution, remember, will remain feasible as long as CJ minus ZJ, right, is less than or equal to 0, right? So if it's less than or equal to 0, then it means that the solution is still optimal. So then we have to determine the change for -2 plus the change is less than or equal to 0, right? So that's what we'll do here. So -2 plus that is less or equal to, therefore the change should be less than or equal to 0. So as C2, right? As C2, so we say C2 is equal to 4 plus the change, right? And now we've seen that for the change to be optimal, this must be satisfied. And we've realized that the change should be less than or equal to 2. So then it means that when we put this change into our problem, right, we can solve and we say that, oh, therefore C2 is less than or equal to 6. So the coefficient of the second variable, right, the solution will remain optimal as long as C2 is less than 6, right? So this is very straightforward. So this implies that as long as C2 is less than or equal to 6, the present basic solution remains optimal. So this implies that S1 will remain in the basis with their optimal values of 4, and ZJ will remain as 24. All right. So 4, 24, right? And this one is S2. The S2 is the non-basis, right? So assuming the value changes, then it means that it would affect the solution. That's what we mean here. All right. So now let's look at the changes in the ZJ when the value is actually in the solution basis. So when we have that as part of the basic solution, or it's a basic variable. So using the same model, right? If there is an increase in this, the initial value is 6, but now we are saying that it increases to that, right? So assuming we solve this initial tableau, right? When we solve this, the final tableau or the optimal tableau will be obtained as this, right? Will be obtained as this. So what are the range of values? Okay, so if one of the non-basic variable enters the basis, then the present solution is no longer, optimal, right? Good. So if in order for the present solution to remain optimal, Cj value for the non-basic value must remain negative or 0. So this one must remain negative or it must be 0. So it means that -2 times the change must be less than or equal to 0, right? So if we are to look at that, then we'll see that x2 must continue to be less than or equal to 0. Therefore, the change is greater than -2, right? Again, the S1, right? The S2, this change must continue to also be 0 or less than 0, right? So then the change is supposed to be that. So by substituting the C1 is equal to the 6 plus the change, right? The 6 plus the change. Then we'll see that for x2, right, where we said the delta is -2, right? When you play the -2, then S1 should be greater, C1 should be greater than 4. And when we put S2, the delta is -6. When you put it here, then you are going to get C1 greater than or equal to 0, right? So then by combining the two, we'll see that C1 is greater than or equal to 4, right? So this one too is the same thing. You can use the normal line to just appreciate this whole idea where we have C1, 2, okay, let me start from 2, 4, 6, 8, 10, right? And we have, I want to just erase this, and I want to change my pencil marker to, let's say, to blue, right? So C is 4. So anything greater than 4, right? Then anything also greater than 0. So assuming the 0 is here. So it means that the converging point is this, anything greater than 4. That's why we have this value well written here, right? We have this value well written here. So usually, when it comes to this solution, it's very easy, the sensitivity analysis. So this is the understanding of it, right? And when we initiate our computer solution for linear programming problems, you'll be able to appreciate that, right? You'll be able to appreciate that. So in a typical scenario, we'll be provided with a final tableau with the changes, and we'll be able to determine the range of CI values or the range of BI values that will continue to let the solution be optimal. All right, so at this stage, I want to thank you for staying with me. So in our next video, we shall look at solving linear problems with computer applications, and then we'll be done with linear programming. Now, we spend much time on linear programming because linear programming is the foundation of operations research, right? So when you understand the linear programming formulations, their solutions, then you'll be able to understand the several forms of the operation research problems or challenges, like the transportation problem. We can solve the transportation problem using the linear programming approach, right? But there is also a different form of a different approach in solving the transportation problem. You can also solve the assignment problem and what have you, right? However, when you understand this, then you'll be able to understand all the various forms of the linear programming, the operation research problems, right? And I believe your foundation will be stronger to be able to solve high complex problems. So on this note, thank you very much for staying with me, and we'll meet in the next lecture. Thank you.